cooking now? Was I able to? I had to go over there to turn like the front light off, right?
Oh yeah.
Second time. Oh, it's literally either on or off.
No, you turn it off and then click the arrows.
Oh, okay. So that.
Sure.
Mood lighting. But I can still. Wait, is this what? Is this turquoise? What's the color?
It was like. I think they just used blue, but it turned out more of a teal.
He's going for the Oompa Loompa look. Nailed it. Definitely nailed it. Okay, so having said that, then let's go back and bring up the. So we'll go a little bit out of order for what I thought I was doing today, but that's okay. We'll wing it. All right, so you've looked at introduction, environment setup, and basic syntax. That's the sections you've looked at? Okay. So then let's go ahead and did they have you actually write anything with basic syntax?
They showed it to you. They didn't like have you do it.
Okay. So everybody has what, NASM installed? Is that what they took you through for environment setup?
They took you through that, but NASM is, they were like saying you need a Linux computer.
Oh, we're going to use Cloud9 with NASM, so we'll get to that. But I want to, so we'll go a little bit backwards. We'll start with this guy. And Curcio is not allowed to answer anything because he just literally saw this earlier today. Okay, so let's kind of look at, well, I'll pause this for a second. Let's go back to and kind of review where we left off last time. So kind of what we're dealing with in here is this idea of performance and how hardware melds with software inside of our computers. So we kind of talked about these different components of our computer, and we're going to talk a lot about the operating system's relationship with the CPU today. We're also going to be talking about more network stuff, which we kind of float out over here. But we drew a little box version of a computer, if you will. And we started going through and we started talking about kind of the history of our various buses, how data is transmitted between 2 points, whether those 2 points are between 2 devices on a computer, whether it's over a network. We talked about all sorts of different things. So we want to get comfortable with this idea of data transfer. All right, so we talked about 2 kind of competing technologies over the years for dealing with this data transfer, parallel versus serial. Talked about the pros and cons of each of those, and then looked at them over the years. We saw from a hard drive perspective, SCSI versus IDE, serial versus parallel, blah, blah, blah. We kind of talked about when serial is better, when we need a kind of a consistent speed prior to the ability for us to kind of buffer stuff. What does that mean? When I say we're now able to buffer stuff, why is consistent speed no longer important? So our original example was, I think we were talking about external hard drives. And if you had a FireWire external hard drive, which was a serial technology, that might be a better scratch disk for something like video conversion or something like that, because you're getting a pretty constant bit rate because it's literally streaming 1 bit at a time. It's linear. Well, that's kind of gone away. Parallel has kind of won where it comes to USB versus FireWire. Why is that idea of consistent bit rate less of an important thing today with buffering? How does buffering actually work? Go ahead.
As data's coming in, you store it in like a little pool, and then it flows out at a constant rate, and if you can keep enough stuff in the pool, then you can always flow out at a constant rate.
Okay, so we're controlling the outflow to always be constant, and worrying about just making sure we have the pool filled up enough that we can always draw data from the pool. So where we run into problems, like if you're watching Netflix or YouTube or something like that, is when you have an initial burst, network burst, where it thinks you are able to sustain more data streaming in than you are. And now it says, oh, okay, well, we're good to go ahead and start draining the buffer. So that's because you're actually watching your video stream from the buffer that's actually draining, when your network actually can't keep up because you have his network. Something like that. Okay. The quiz. So we'll do a verbal quiz today. So last time we talked about this, the dial-up modems. We talked about handshaking. Remind me, what does handshaking mean?
Figuring out the fastest speed they can communicate without losing data.
Okay, without error. Yep. So handshaking between a digital and an analog device is the fastest speed that we can communicate without losing, without having errors. And why did we need that? And I guess another way of asking the question is, why don't we need that today? Yeah, we have recoverable protocols now, right? So we're not saying we're okay with errors, but we can recover from errors. If you're in a network that has tons and tons and tons of dropped packets, you will notice a performance hit. So just because we can recover from it doesn't mean that we want that.
Use UDP.
Huh?
Use UDP and pray it gets there.
Well, UDP only is helpful for applications where the data doesn't have to arrive. Yeah, so I mean, UDP would be perfect for like video. I mean, if you drop a frame of a video, you don't really want to pause the whole video for it to be resent. You'll just miss that frame. You know, you hope that you had enough frames filled in there you didn't even notice. So that's datagrams. UDP. That's the point of UDP.
Yeah, most updates too. If you're sending an update of an entire game or something, the client status, as long as it's the same structure, just the same time, you can fix it.
Well, right. I mean, so that's the point.
Yeah.
UDP and TCP are not competitors. They're not competitors with they approach the problem two different ways. TCP is recoverable. UDP says, hey, I'm sending this data. If it doesn't get there, so what?
But it's faster.
Well, it's not necessarily faster, it just has less overhead.
There's enough of the speed if you're sending enough packets. Because there's no handshaking, there's no verification, there's no knowledge.
Well, there would be no handshaking with TCP.
You say, hey, I have this packet of this size length. Okay, I received your initial request.
Oh, fine. So the complexity of
Right.
a TCP packet
you
is
have to send many packets.
there's not measurable speed differences. The speed difference would be in the data recovery. With TCP/IP, you're guaranteed to have the data ultimately arrive. So with that in mind, you know you're going to receive it. If you're using an application where knowing the data gets there doesn't really help you, video streaming is the perfect example. If you drop one frame out of 1,000 frames, who cares? We didn't notice. We don't want the whole thing to pause while we're resending that one frame for a part of the movie that was 15 minutes ago. You know, it doesn't help us. So those types of applications, similarly with real-time gaming, where we're updating at a pretty constant rate a character's position on the screen. Sometimes you might see a character kind of jump on your screen because they missed maybe a packet was lost or something like that, a datagram. So TCP uses packets, UDP uses datagrams. Kind of the same thing. They're just lighter weight things. But the idea would be if we miss one, fine. We're not going to go back and find out where that guy was one pulse ago when I'm going to get the next location for him in a second. So we just have two different approaches to the same thing. But before we even had the technology for TCP/IP, effectively everything was like UDP, except even when we did care whether the data got there, it was like UDP. It was not a recoverable thing. So again, performance is an issue. So we talked a lot last time about this idea of speed, and What does speed mean? What does good mean? What does performance mean? And we're going to talk more about that today as we start talking about how processors are actually built and that kind of stuff. And we saw that we had a bunch of different kind of angles into speed last week. We talked a lot about our internet connections. What makes your internet connection good? We went around the room, and depending on your application, some of you wanted low ping if you were an online gamer. Some of you wanted high bandwidth if you were a movie thief. That kind of stuff. So there are different ways of measuring it. So if you're somebody who steals a lot of fine, we'll remove the word steals. If you're somebody who downloads content off the internet, having a high latency internet connection is not a problem. Fine, it takes an extra 10, 15 seconds for your download to start, but you're going to walk away for an hour while it's downloading. It doesn't matter. But that's unacceptable for real-time gaming. It becomes a problem. So we talked about that. We talked about what does good mean. Kind of our comparison between CPUs and GPUs, and this is where we started segueing towards our paper that we worked on. So really we're talking about a general purpose collection of circuits versus domain-specific collection of circuits, right? So GPUs are really good at math. They do a lot of floating point math very, very quickly, and because of that, in a similar real estate footprint, we can fit more of those circuits, more of those cores on a GPU than we can on a CPU, because the CPU has, let's say, 100 magic tricks it knows how to do. A GPU, let's say, knows how to do 10. So we can duplicate those 10 times in the same footprint. Let's just use that as simple math. Okay, so we started talking about the nature of the CPU being kind of a collection of circuits. We talked about this idea of a programmable microcontroller. So remind me, what's good about a programmable microcontroller? Why is it kind of the best of both worlds? What problem is it solving for us?
You get the specific circuit structure that you want, but you can change it.
Okay, so you can change it without a soldering iron or screwing with wires, right? So you can you can kind of build your logic in software, which does add a layer of overhead. It will slow it down. Programmable microcontrollers are slower than just raw hardware. But perhaps for most applications, not enough slower to make it worth moving away from this, since we can fix problems pretty easily, especially when we talked about firmware. Pretty often we'll have the firmware get updated in our routers or something like that. So if they find a bug or there's a performance update or something like that for your router at home, you don't want to have, you don't want them to send you a net message saying your router is no longer safe to use, go to Best Buy and give them more money. It would also be kind of funny but weird if the Linksys tech came out to your house to replace a board inside of your router. But they do that for TVs, which is kind of interesting. But that would be weird. So now you can just download a software update, which updates the programmable microcontroller inside of your Linksys router. All right, so we talked about some of the, we talked about Arduinos specifically being programmable microcontrollers. There's a whole bunch of them out there. We talked about firmware. All right, then we started talking about assembly language being a low-level language, one-to-one relationship with the CPU. And we kind of, this was a thing from the book, so I'll give you your first reading assignment from the book today. But this was a pretty interesting statement, I thought. If cars had changed at the same rate as computers have evolved, we would be able to drive from New York to London in a second for a penny. Kind of an interesting statement, and we're going to segue off of this for a decent portion of our discussion today as we start moving towards multiprocessors and thinking about why we did that and that kind of stuff. Forget that for a second. Okay, so I think we sort of stopped right around here, right? Okay. But I think that I don't think you've seen these slides. Yeah, so we're fine. Okay, so with that in mind, let's go back here. So before I kind of dive into this code, tell me what you learned in your assembly tutorial dealio. So kind of give me the overview. If you were giving me a crash course on the first 3 chapters or first 3 sections of this assembly thing, what can you tell me about assembly that you learned?
Essentially one level above just typing in binary.
Okay. Why do we need that one level above?
So we're not just typing in ones and zeros.
Okay, and why do we need that? So he said so we don't just have to type in ones and zeros. Would we be very good at typing in ones and zeros? We would be error prone, right? Now, it's not that we're saying assembly is easy, but it certainly looks way more English-like than ones and zeros, right? All right, tell me more. So we have this language that sits at an even keel, an even level with the CPU. We're just speaking English-ish, and that gets translated into, it gets decoded into an equivalent single instruction on the CPU, single magic trick on the CPU. Why would we want to talk to the CPU on a one-to-one basis as opposed to a high-level language like Java and all that stuff?
Gives you a lot more control.
Okay. Defend that.
Like you have access to a lot of things that a lot of high-level languages would maybe prevent you from touching.
Okay. So at the end of the day, a high-level language, when you compile it, is going to translate into a whole bunch of instructions in a low-level language. So every one line of code in a high-level language translates into potentially many, I like to refer to them as magic tricks on the CPU. Fair enough. All right, so you don't have control over that compilation step, right? You don't get to choose which exact assembly instructions come out of these 2 or 3 lines of high-level code. All right, fair enough. So you have granular control over it at the cost of you having to write 30 lines of assembly code, or just as a quick glance here, this is hello world in Linux assembly, as opposed to just system.out.hello world or console.writeline.hello, hello world, if you're doing C#. So I mean, instead of one line, it's that, which was just okay. Why? Okay, so you mean the entire time is less because you don't have to compile it first. Okay. Okay, fair enough. But would you say that it's probably also going to take us longer to write the assembly language version? So we replace the convenience of the compiler with the slowness of a human being having to type in extra lines. Okay.
When you write a code request to process a machine instruction which leads to any rocket scientist, some kind of big task, it's better to write it into the processor language rather than using other application language.
Okay, but won't a compiler ultimately translate our high-level language into the processor language? Won't it translate it into assembly?
Yeah, it still takes some time compared to other things. If we are looking at the writing side of the code, it takes a lot of time. But when it comes to
You mean the time it takes to compile it?
takes to generate the instruction set from the high level language.
Okay, fine, that takes time. But once that's done, and we actually have the instruction set, have the assembly code, this assembly code isn't any better or worse than this assembly code over here that we wrote, other than programmer efficiency, right? The idea would be that more than likely a modern compiler is going to create pretty efficient code at the assembler level, whereas us, we maybe can keep up-ish, but chances are we're going to have some weakness in our assembler from an efficiency perspective. So I don't know if we've gotten to the idea of why assembler yet. I don't think that's a good argument. I don't think the argument is well, why should we write it in assembly versus writing it in a high level language? Because the high level language is going to take time to compile and ultimately it'll run on assembler. Who cares if it takes time to compile? Once we compile it, it's good to go, and now it runs on assembly. It's running natively on the hardware, and everybody's happy. So That's not a great reason. It leads to some understanding, but why would we actually want to write something in assembly? But
So, well, two main reasons, I guess. It's first off, you're targeting a specific set of hardware or a specific chipset.
okay,
So you know exactly what you're outputting and the quirks and everything else are against that versus a compiler kind of taking a general broad stroke at this is the architecture that we support.
okay,
And then the second one would be that you then have access to the full hardware. So if you were to write something which has access to another chipset or another processor on it, you don't have to go through a third-party application or something like that. You can directly write to that other module.
okay. So that kind of goes back to what Tim was saying, is that even though a high-level language compiles down to a low-level language like assembly, you don't always have access to all the things you might have access to if you were writing it at the assembly language directly. That might mean various parts of a microcontroller if you're using some sort of proprietary system and you knew about it, or if you're using a general purpose Intel architecture or something like that, you aren't having to play the game that Java or .NET uses to translate your high-level language into a low-level language and what it's protecting you from and that kind of stuff. You have direct access to everything. With that power then comes the responsibility or the inconvenience of having to write more code. Okay. Anything else? I think that's a significantly more reasonable response.
Less memory usage.
Okay. Why would it be less memory usage?
We're directly talking to the executable instructions rather than via an external application.
Okay, so kind of back to the same example of the compiled thing, and so I guess in my mind I just move past the compiled and say, okay, well, we decided to use the compiler. Who cares? Anything that happened over here is now gone. We're at the assembly language thing there, but I do think whether you're going in this direction or not, that is kind of in the right direction of where I'm heading with this, and that is sometimes the assembly code. I said a few minutes ago that we would expect that our modern compilers created by super smart people, blah, 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 that have been time tested, whatever, would produce very good assembly language, right? Very efficient assembly language. Do we all agree with that? Can you give me an example or a scenario where a compiler might produce non-ideal assembly language?
Where the deadlock occurs.
Say this again.
Where the resources allocations differ with the request, like deadlock cases occurs.
Okay, so why would that? I mean, so are you saying that the resources on the system might be in a certain state?
Certain state they were not reachable, so that using a machine language we can directly talk to them instead of using a compiler and going into the.
Well, but you're still going to come down to the machine language. I mean, the compiler produces. I mean, if we kind of draw a picture here, just so I'm make sure everybody's kind of on the same page with this. You know, if we have, you know, in honor of Haxton, we'll use C# as our example. So we'll say he's kind of a Microsoft fanboy. So it's a
Kind of.
well, that's fair enough.
I don't like one though.
This is one application.
OneDrive, that's the one.
All right, so you know, you take this guy through a compiler. All right, and ultimately, this guy then produces assembly. All right, and assembly should be orange, of course.
So we probably should use C++.
Well, it's still ultimately Microsoft Intermediate Language, which ultimately becomes the assembly, so it doesn't matter.
Fine.
Or,
You want to skip that?
oh, okay, you want to? Hey, I was doing C# for you.
If
Okay, you want to be picky about it, it's fine. Yeah, what he was pointing out is technically the .NET component architecture compiles this guy down to Microsoft Intermediate Language for C#, which then at runtime, the very first time you run it, turns it into actual assembly. So from that point forward, it's assembly. But hey, you know, he lost his opportunity, so there we go. All right, so this would be if we were taking a high-level language, compiling it, and turning it down to assembly, versus just writing assembly directly. Okay? My question here is there a scenario where our assembly, this guy right here, we'll make ours italics and bold. Definitely tell the difference now. Is there a scenario where our assembly could potentially be better, more efficient, whatever, something like that, than the assembly produced from this compiler that's evolved over many, many years of people doing work on it, made by really smart people, blah, blah, blah? Can you give me a scenario where this assembly is preferred to this assembly? Go ahead.
Correct me if I'm wrong, but doesn't Java auto-allocate 4 bytes of memory for each byte, double, whatever you're doing? So that even if you are allocating a byte, it still gives you the 4 bytes worth of memory?
But only in the virtual machine. At the hardware level, it's still going to be, it's going to deal with data bytes and stuff.
Well, I guess the same thing applies, is that you have access to the full extreme memory. You know what's exactly going to be in there, so you can
fair enough.
reuse memory and reuse allocation, whereas you have to play with the garbage collector in Java or C# or something like that.
Okay, so that's your argument that this might not be as good as this?
Right.
Okay, I think that's kind of a crappy explanation.
Well, it is to some extent.
It is crappy, or?
Yeah.
Oh, okay. I think Alex agrees. Right, old Alex?
Well, I mean, if you don't have the capability of running the garbage collector or the framework, whatever you're using, then...
Well, but forget about that at some level. I mean, we're looking at 2 different assembly programs. One was produced by a human being, us. It's the bold italics one. One was produced by a robot, this compiler. We're just now looking at that world right there. We are trying to solve the same problem. We have written an assembly program to solve problem XYZ. Over here, we wrote a high-level program to solve problem XYZ, which then got compiled by the smart people compiler, which produced a correct assembly language solution for solving problem XYZ. Why is our solution, what's a scenario where our solution to problem XYZ is superior to this solution to XYZ? Go ahead.
I read about a statement like interrupt service routines. Assembly language is better for interrupt service routines than higher level language.
But we could forget that this stuff even exists. We have assembly language. We're comparing our assembly language to the robot's assembly language right here. So from our perspective right now, that stuff is gone. All right. Robot's assembly code, our assembly code. It's assembly. Just 2 different, potentially different, solutions to problem XYZ. Go ahead.
Memory assignment?
Okay. Sounds made up, but go ahead.
I mean, in the sense of like when you are writing specific assembly language, you yourself choose the locations of where to store whatever. Whereas a lot of times when it's been converted or whatever used from a high level language on down, it's not, it can be randomly thrown around.
Okay, fair enough. So let's go down that path. So you're saying that your choices of where to put something might be better than the compiler's version of where to put stuff in, and kind of a generic creation of assembly. Okay, give me a scenario where that would be true.
Lists, example.
Okay.
Because it's just connecting various points in memory, but if you, for example, put them in memory like fairly close together in a somewhat organized fashion, the computer can probably...
But you don't have control over it. Oh, I get it. You would have control over that at the assembly language
Right.
level if you literally grabbed a whole bunch of memory next to each other. But so I don't know that you're entirely wrong. I think it's maybe a mediocre minus example, and the reason for
it's a really minute detail, but it's kind of...
But it almost breaks the reason for linked lists. Remember, the purpose of a linked list is, as opposed to an array, we can just grab a bunch of memory and say, okay, well, we have contiguous memory, so it's going to be fast, but now we're limited. We can only fit so much crap into this array. With a linked list, we can hold arbitrary amounts of data because this guy links to this guy, which links to this guy, which links to this guy. By definition, linked lists don't necessarily live next to each other in memory because we don't know. So if you're writing a linked list in assembly language, you don't necessarily know the nature of your data. If you knew the nature of your data where you got to pick the exact memory location, you might as well do it as an array. It's like, well, we'll just put it all right next to each other. It's fast. So really what you explained is why arrays are fast. But kind of leveraging off of that, you're right. You do have control over the exact memory locations you might use, the exact registers you might use. So can you give me a scenario where that control is beneficial? And I might actually be sending you down a bad path with that because it's not necessarily related to what I have in mind. And you guys should be able to come up with what I have in mind. I'm looking for a scenario where, in fact, I'll give you a hint. There are scenarios where this assembly language does more than it needs to do. And our assembly language can streamline stuff and do less because we know the nature of the problem.
When you know something's not going to get hit.
Okay. Yeah, I think we're onto something there. So
like safety checking?
Well, I mean, I think safety checking is kind of the good example here. How often in a high-level language has the language kind of forced you to do something, write a little chunk of code that you know will never be reached? Like, hey, look, it wants me to return something here. I know for a fact it's going to return up here, but it's not going to let this guy compile until I put a return statement down here. Even though I know, because the nature of the data, we will never get to this line.
Null checkers and that sort of thing.
Well, sure. So there are times in a high-level language that we need to play by the rules of C++ or Java or C#, and because of that, it's going to produce accurate assembly code, but that might have additional bigger memory footprint, a couple of extra questions that need to be asked. This kind of goes back to the approach to how human beings solve problems. We remember stuff, we ask questions, we use repetition. And all programming languages have facilities for mimicking that. All right, so every question that we do, every Boolean expression that gets executed in our program equals time. So the more Boolean expressions, the more time a program takes to run. So if we can remove even one question, we're increasing the speed of that program as long as we didn't add. we removed this question but added a whole bunch of fluff over here that made it slower. But if we can go in and streamline the assembly language, removing the extraneous pieces that the high-level language forced us to put in, but at the low-level language, we happen to know those parts of the code will never get reached, even though they were produced by the compiler. That would benefit us. So the example I like to use is in some video games. This is where assembly is still used today. You might have some parts of a video game that need to be really, really, really fast. And even if most of that video game is written in a high-level language, perhaps the low-level code that was produced for a certain section of the game has a bunch of error checking that the programmers of the video game might say, while it's possible that stuff will happen, if it happens, the program's going to crash anyways. So given that, we might as well take all that error checking out, hope it doesn't happen, that way at least it's fast when it doesn't crash. Okay, I'm pretty sure that's the approach for most of these new indie games. What's the acceptable number of crashes per hour for a new game? It never used to, like a PlayStation game comes out and the thing is like unusable, it crashes. Like, that didn't happen. Like when I was a kid and a Nintendo game came out, they didn't crash.
Games are much simpler though.
Well, not necessarily. It's all relative. mean, they were running the games back then. In fact, it's quite possible the games back then, compared to the hardware they were running on, may have been more complex.
That's true, but there's more fluff to it.
More bells and whistles,
Right.
more moving parts, where
Yeah.
more things could go wrong.
Yeah.
Okay.
It's not like in the old days where you can spend literally a month looking at 100 lines of code, and that's like the majority of your program. Like you gotta figure out, okay, we have this big vast universe or whatever, and figure out why this is interacting with this graphics card wrong and whatever else.
Mm-hmm. I don't know why this reminded me of this, but it's related to technology and programming, so I guess it's close enough. But I wonder how this would happen in today's world. So, any of you ever play Mike Tyson's Punch-Out for Nintendo? All right. So, so I mean, I loved that game when it first came out. Well, during that time when the game was still popular, Mike Tyson went to prison, right? They changed the game and turned Mike Tyson white. They did. It's just called Punch-Out. Yeah. So they made him. The whole rest of the game is identical, except you had a white Mike Tyson, and it was no longer called Mike Tyson's Punch-Out. I wonder how that would play out in today's society. Like, it wasn't even news back then. You know, today you'd have somebody rioting over it, wouldn't you? Yeah, I found that.
Oh my God.
Yeah, I don't even know why that came up. I was just thinking about, what's this?
Someone would get shot.
Yeah. I remember, like, when people used to return Nintendo games, they had a little tool for opening up the case to make sure you didn't remove the chip. Because what people would do is they'd buy a Nintendo game, and they would basically have one Nintendo cartridge they owned, and they would just have chips for all the other games, and then swap out the chip for when they put the Nintendo game in.
Oh, it's like
The employees at Target do that now. They don't check your, your Game Boy to see if you removed the motherboard. You just give them this empty husk. You basically filled it with Play-Doh and put a fake screen on it.
that's a wager.
That feels about right.
Why is this Game Boy oozing?
It's like most people use Play-Doh. You had to use slime. Well, the Ghostbusters movie just came out. I assume they sold slime, didn't they? They had to have. Ghostbusters just came out. They had.
Sure Ghostbusters was just a gigantic flop.
Did you see it?
No.
It actually wasn't bad. I had my expectations were incredibly low. Let's start off with that. My expectations
Was Bill
were.
Murray in it?
He had a cameo, yeah. Yeah. The movie was better than it should have been. It wasn't as good as the originals, but it was better than it should have been. Yeah, I actually thought it was,
Based off the trailers, it just looked terrible.
yeah, I agree. Totally agree. I went in with zero expectations. So I went in assuming it was going to be a 0 out of 10, and I would probably give it a 5 out of 10. It was watchable.
Pretty generous.
Yeah, and one of the characters actually I thought was pretty good. Like one of the 4, I think she's the one that's kind of supposed to replace Egon, like be the weird one. I don't remember the actress's name, but yeah, she's pretty funny in it. So I would say if you could just have 4 Ghostbusters like her, that would be a hit. It's incredibly unstable.
You gotta do the green screen thing, so it's just her 4 times.
Yeah, but she was like the one who makes all the gadgets and stuff like that, and not really tested well, and kind of surprised when things happen, whether they happen right or they're wondering whether somebody should have died, and she's looking at it like it's a science experiment, not realizing humans are involved. So I thought it was pretty good. All right, so in any case, if we have a video game where a specific part of the game needs to be very, very, very fast, and we decide we're going to go in and we're going to look at the assembly language that was created by the compiler, and we're going to go in and we're going to modify a little part of it and say we want this to be really fast, so we're going to take all these questions out of here, all right? And assuming everything goes right, those questions should have been extraneous anyways. Game could crash sometimes if moons align incorrectly or other parts of your application suck, but point is this one part will likely be very, very, very fast when it works. Or as fast as it can be when it works. And And I mean, how many of you have played video games before where a game works on your computer or whatever very well most of the time? And there's like one or two scenarios where it's like, this is unplayable in this one place. You know, I use World of Warcraft as an example because it's the game I have the most experience with, where, you know, there were, especially in the earlier days of WoW, the game would run fine on your computer, but if you went to a certain city, unplayable. Yeah, I mean, you know, frames per second would drop to nothing. There was too many particle effects, you know, whatever. You know, but it was only in that one place. Everything is, I mean, so what are you supposed to do? Tune, because now all the games have the ability to like tune your, you know, the settings down so it's playable on all sorts of different hardware, right? So are you supposed to tune your hardware down to nothing when you can have it on almost high most of the time until you walk through the wrong door and then you no longer function in the game? So there are aspects of games that can benefit from micromanaging certain parts of it in assembly language. Kind of make some sense? All right, so that's a argument for when assembly language could still be useful today. At the end of the day, no matter what we're doing, we're always using assembly language today, right? I mean, it's happening whether we wrote it directly or not. It's still involved. And that assembly language then gets decoded into the underlying binary. All right, and so based on what you read, tell me about that. So there is a I assume in your reading for those 3 sections, you read about decoding an instruction. Probably talked about fetching an instruction, then decoding an instruction. It had to have done that. Okay, so the execution cycle is fetch, decode, execute. Okay. Okay, so when we fetch an instruction, this is get the assembly language instruction. So looks like assembly language, looks English-like. Decoding is translate from English-like to, let's call this machine language. It is binary, but it's binary for some different reasons. So let's talk about the nature of that. When I decode an assembly language instruction, so for example, let's just take a simple instruction that's probably one of the examples you saw in basic syntax, like move AX comma BX, something like that. Is that something along the lines of something you saw in the reading? Okay, so this would be a English-like assembly language instruction, where we are calling the move instruction, and we're moving the contents of this register into this destination. So the contents of BX will move into AX. Make sense? All right, so now to decode this, we need to translate this guy into machine language. What does that mean? We advertised last class that a CPU is effectively a collection of circuits, collection of integrated circuits, right? And I refer to them as magic tricks. So each of those magic tricks has a name. One of those magic tricks is going to be called move, okay, on that circuit. So if you think about your CPU as being like a town, somewhere on that town is going to be a little building labeled move, okay? And how do we know where that guy is? So you have the physical town sitting here. All right, so if we draw a picture of this, love these pictures. So this is our CPU. All right, and on the CPU, we have a bunch of different integrated circuits kind of floating around different places. This is a very simple CPU. It only has three instructions. This is like Bob's CPU. You ran out of solder, and this is where it ends. Okay, so up here, this is where our actual move instruction is. All right, so this is our move instruction. We're looking at a kind of a Google Maps version of our CPU here. Somewhere, we need to have some documentation that says the location of that circuit, so that when we actually need to send input into that circuit, where is it on the CPU? Now, how many of you have ever held a CPU in your hand before or seen a CPU up close? Okay, so what does the top of the CPU look like? Just flat silicon things, and there's the metal piece for like a heat dissipation, right? What does the bottom look like? Zillions of pins. Bunch of pins. And each one of those pins, well, let's go with, what are those pins? What's the point of those pins? Okay, so the pin on the bottom of the CPU, well,
Like AMD
fair
has
enough.
the pins on the
no, fair enough. So there are connections to the motherboard, but stuff will flow both directions on those pins, right? So some of those pins are going to be used as inputs into the CPU. And what are those inputs going into?
They are like nodes to the different parts.
Yeah, so inputs to our magic tricks, right? So if move requires two things, two inputs, we're going to have to give it those two inputs, right? And there's going to be pins for getting that information into it. So that's one way to get stuff into the CPU. So we're going to have a, let's just say it's a text document somewhere. And this move instruction, let's just say, to keep it simple, that move instruction is instruction 1. All right, so that guy will decode to instruction, let's just say, since we have a very simple CPU here, our instruction set is 4 bits. So that's that. So if my instruction set is 4 bits long, what's the maximum number of magic tricks I can have on the CPU? This is a 4-bit CPU. Close. Zero to 7 is the range, so 8. Yeah, 8 unique instructions. So I can have 8 unique instructions on this. Good thing is Bob ran out of solder. We only have 3. We got room to work with here. All right, so instruction number 1 on this is move. So when I decode the English-like move instruction, it's going to translate into the assembly, or I'm sorry, the machine language of 0001. Make sense? Now, move actually, as I had it written, was AX, comma, BX, like that. So here is the instruction part of it, but now we need to give it the address of our registers. All right, so we're going to say everything is dealing with 4 bits just to keep this relatively simple for address space. So that means that this, well, realistically speaking, we would probably do this as, well, let's keep it 4 bits. So that means we have 8 different registers in a 4-bit, the possibility of 8 different registers, and we'll talk more about that here some point tonight. All right, so when we move AX and when we move BX into AX, after we have our instruction, we're then going to have to say what the next 4 bits will be the mapping of what is AX in terms of my list of registers. So maybe AX is register 1 and BX is register 2. That makes sense? So you might have something that looks like this. So decoding move AX BX might look like this sequence of binary bits. And that's what actually runs on the CPU. It says look up instruction this. Go to this address on the CPU. Then feed it. This is one input. This is the other input. Make sense? And that's going to be relative to the pinouts on the bottom of the CPU. And we're dealing with this at the high level because we've kind of fictitiously created this 4-bit CPU. But roughly speaking, that's how it works. Make sense? All right. So that's what decode does. Decode is kind of like compilation, but typically when we talk about compiling, we're saying we're going from a high-level language down to a low-level language. Decoding an assembly language instruction translates from a low-level language to still a low-level language, but I suppose it's to machine language. Technically, we couldn't say machine language is a low-level language because it doesn't have a one-to-one relationship with machine language. It is machine language. So think of it however you want, but it's at some point, you know, we can't break it down more than it is. All right, and then execute, kind of self-explanatory. It's once you have it, you know, kind of ready to go, we actually have it set up in machine language, it's ready to fire, then fire. Okay, so now let's go and look at the nature of our assembly language. So here's some instructions. So this is for Linux, and we're going to be using Linux in here. We're going to use a thing called Cloud9 for getting our assembly instructions. That way we're all using, you know, a consistent environment. You can actually get NASM for the Mac if you want, but you're going to see that there's actually a problem with that if you have a Mac and you get NASM for it, unless you use the 8086 emulator to mimic a generic 8086 processor. And that'll make sense to you here in a few minutes as we talk about this. So what we're looking at here is the Intel architecture. I'm not sure which version of the Intel architecture this assembly is for. It's certainly a newer one since it has EDX, ECX, as opposed to the old school processors like the 8086 processor had AX, BX, CX, DX. So now we have an additional, these are 32-bit processors, or 32-bit registers for doing stuff. That'll make sense when we talk about it a bit more, but this is going to be a newer Intel architecture, but this is Intel. What other architectures are there besides Intel architecture that you've heard of?
AMD.
Okay, AMD is still Intel. It's an Intel compatible architecture. AMD is Intel compatible.
All the time?
Yeah.
Really? Huh.
Yeah, I mean, you can install Windows on a machine with AMD.
Yeah, that's true.
Yeah. AMD has a couple of like tweaks to their architecture that allow, there's some AMD specific things that if the software takes advantage of it, there's a couple of instructions it understands that an Intel doesn't have built in that may or may not be useful, but it's a superset of Intel. Well, let's say it this way. It's a superset of Intel so far as to say Intel licensed its architecture, because Intel also has its own proprietary stuff like hyperthreading, for example, is our hyperthreading is to an Intel architecture as AMD's extra crap would be to an Intel architecture. So AMD, another company that makes Intel architecture compatible processors, because you don't have to go and get the AMD version of Windows to install on it. All right, so what other architectures do we know of? Might as well create a list of this.
There's ARM.
CPU architecture. Nailed it. All right, so we said, did I? Oh, thanks. Sorry. All right, so we have Intel. Now, usually Intel architecture is IA. So if you ever see a processor, you might say IA R6 or something like that. That's like revision 6 of Intel architecture. You might say IA Core 7 R6, that kind of stuff. So that's showing you the who the core architecture is Intel architecture, and then the sub-architecture of it, Core i5, i7, i3, and then revision of that. So for example, Core i7 processors have been out for a while, since like 2011. Certainly 2012. I think the first one was late 2011. But if you buy a brand new machine today, chances are your top tier processor is going to be a Core i7, right? Is that the same Core i7 that was out in 2011? We hope not, right? Now the reality is it probably has a whole lot more in common with that than we think it should. And we're going to have that discussion probably after our first break when we start talking about multiprocessors. But is it reasonable to think in that time period between 2011 and today they've made some tweaks to that architecture? Maybe they've gotten a little bit better at squeezing more stuff onto that same real estate, or with heat dissipation, where maybe they've bought themselves a little bit of extra space to throw a couple of more magic tricks on there that maybe optimize things. Reasonable assumptions, right? I don't know the exact details of what has changed with the Core i7 processor today compared to 2011's version, but it's reasonable to say that they are probably not identical. But today's version should be at the very least, either equivalent or a superset of the architecture that was in the Core i7. Similarly, the Core i7 architecture was a superset of the previous Pentium architecture. Or I guess before that was the Core 2 Duo. Core 2 architecture. Duo was just multi-core. But these are all supersets of each other. So if you had a program that ran in DOS from 1995, would that program presumably still work on a computer today? On a Windows machine today? Yeah. Depending on how poorly the program was written, it may not be usable. When we think of the example I've used in other classes, did I mention Double Dragon in here last time? I think some of you have heard this example before, though. One of my other classes. But so when I was a kid, there was a game in the arcades when those existed. So I played Super Mario Brothers 3 in the arcade. Isn't that weird? Like, you don't think of a Super Mario Brothers as being in the arcade, but yeah, it was. So in any case, there was one of the most popular games in the arcade back when arcades were popular was a game called Double Dragon. And my brother and I were ecstatic when we were able to get Double Dragon for our computer. This was like when home PCs were like kind of new, like we were one step ahead of the Commodore 64. All right, so we got Double Dragon on truly floppy disks, the 5 1/4 inch floppy disks, and had it on our, it ran on an IBM DX2 66 megahertz processor, 486. So 486 was the predecessor to the 586, which was the Pentium, the first Pentium processor. So the predecessor to the 486 was 386, then 286, and the x86. All right, so and all those are supersets or subsets, depending on which direction you're going. So if something was written for the 486 architecture, it would still run on our computers today. Well, so we had this, actually, the example I'm giving you is even, I guess, worse. The problem was seen on the 486. We actually had that on a floppy disk on an old Epson computer. This is when Epsons made computers. Epson just does printers now, right? Or do they even do printers anymore? Is Epson still a company? Just printers? Just printers? Okay. Yeah, well, there's all sorts of interesting examples of companies that almost invented the latest, greatest, coolest computer, but decided the real money was in copy machines, like Xerox, the Xerox Star, that ultimately became the first Mac OS for the first mouse keyboard, mouse-controlled GUI interface. That came from Xerox, who decided the real money was in copy machines, not computers. So, well, back then, who would have known, right? The same thing we go in the, when you talk about investment, people say, well, if you had just put $5 into Microsoft, when Microsoft first went public, that would be worth like $1 million today. I think that's true. It's either $5 or $50, but not a lot of money would be worth $1 million today.
Or it's like the guy who bought what was it, like 150 some Bitcoin or whatever when it was like pennies.
Well, yeah, he was doing a research project, and he found it later on. But punchline is so fine. You can look in hindsight and say that if you had spent $50 on Apple or on Microsoft stock day one, you'd be have $1 million now. Well, fine. Or you could have also just thrown $50 out the window. Hindsight's always 20/20, right? We didn't know Microsoft was going to be anything, so it's easy to say that in hindsight. But in any case, I think that we had gotten Double Dragon on the floppy disk when we had the Epson, which was a x86. Might have been a 286. I think it was a 286 SX 25 megahertz processor.
Oh, wow.
Megahertz, not gigahertz. Megahertz. And it ran great on that. And so my brother and I were, you didn't have joysticks yet, so you had companies coming out with really ghetto joysticks that sort of kind of worked. So you mostly had to use the keyboard, but whatever. Well, so when we got the, I think it was in 1994 or 5. I think 1995. We got the 486 DX2 66 megahertz chip. We had to wait for them to release the chip. It had 8 megabytes of RAM, this computer, and a 420 megabyte hard drive. I mean, this was a beast. This computer today would be equivalent to if you went out and bought the maxed out Alienware. That's what that computer was in 1995. So we installed Double Dragon on it. We were cool, so we had the 3.5-inch floppy, but we also had backwards compatibility with the 5.25-inch. Where you stuck it in, you had to pull the handle down to lock it in. Tried to run Double Dragon. What do you think happened? Pretty much. I mean, probably the folks who wrote it did boss delays and stuff like that, all based on busy wait for loops. So basically, the amount of time it would be until the next enemy came out would be however long it took, a for loop to run through 1,000 times, which on that old machine was a decent delay. On the new machine was a blink. Yeah. And it was a fast blink. so your guy was uncontrollable because everything was hyperspeed, and you had every enemy in the game on top of you at once. So yeah, it was rough. But in any case, that kind of shows this the backwards compatibility stuff. All right, so we have Intel architecture. You mentioned ARM. Okay, tell me about ARM. What is ARM?
Relatively new kind of. Actually, I don't know if it's new, but it's mostly for Raspberry Pi. There's some versions of the Pis. I think the 3 is Intel.
Yeah, it is. Most of our mobile devices today are running on ARM chips. So all those, if you're running, how many of you are Android phones? Relatively new. So the chip that's in your phone is more than likely something called blah 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 Snapdragon. So it's either a 6-core or an octa-core Snapdragon, which is an ARM processor. Apple's chips, what they make themselves, the A7, A8, A whatever, blah blah blah, also an ARM chip. They make it themselves, but it's an ARM-based architecture. It's a reduced instruction set architecture. So we're going to throw this in here. This would be a RISC architecture as opposed to Intel's architecture, which is an expanded architecture. So if we kind of go back, how many of you have heard of PowerPC? Okay, when was PowerPC? What is PowerPC? Who used it? When was it? How many cheeseburgers did it have? Just seeing if you're paying attention. 42 cheeseburgers. And we'll take our first break here in a few minutes. Let's just get through this slide, and then we'll actually get to the assembly stuff. That's pretty common for my MO, right? 3 minutes in the class, we're going to talk about this, and then we have filler. It's here's 15 slides that were created until we can get to that, and then we have to take a break. So when was PowerPC? And who used it? Apple. So they were made by IBM. PowerPC chips were an IBM component, and they were running in Apple computers. And these guys used a reduced instruction set architecture as well. We'll talk about what that means after the break. Let's get a couple other ones on here. So here well, somebody remind me after break that at some point I need to talk about reduced instruction set versus Intel architecture, i.e. non-reduced instruction set. Any other architectures? You heard of one called MIPS architecture. Another one is called the Spark, which is made by Sun Microsystems. They had their own chips called Spark chips. Then they started using Intel processors. We can go on. There's more, but this gives us a kind of a popular list type thing. Now, each one of these architectures will have its own assembly language, because each of these architectures. Now, when I say architecture, what do I mean? What's architecture kind of a synonym for? What am I actually talking about when I say an architecture?
What are the different sets of calculations they can do?
Okay, I think fair enough. But basically, what is the list of magic tricks this guy knows how to do? So the Intel architecture is going to have this list of magic tricks. The ARM, there's actually multiple versions of ARM. ARM is more of a type of architecture as opposed to an actual architecture, but it's pretty much you have the Snapdragon ARM architecture today, but they have their list of things. Now, do we suspect that ARM chips can do things that are similar to Intel chips? There's certainly going to be crossover, right? But all processors are going to need to be able to do some subset of stuff. Similarly with PowerPC, MIPS, and things like that. So to take us to our break, one thing to remember when we come back is that each individual hardware architecture will have its set of magic tricks. So what we're going to look at right after break is we'll finally go and look at a Hello World program dealing with Linux, and we're going to see how does each operating system play into that. Make sense? All right, so let's take 10 minutes.